we start a new chapter on refraction. Now, refraction and reflection are two important topics in geometrical optics. Optics means study of light and related phenomena, and there are two branches of optics. One is called as the geometrical optics and another is called as wave optics. In geometrical optics, which is also called as ray optics, we assume that light travels in a straight line, and that directed straight line is called as a ray of light. And in wave optics, we assume that light is a wave, it behaves as a wave. There are several optical phenomena associated with geometrical optics and wave optics. In geometrical optics, we study two important phenomena: reflection and refraction. Our discussion today is related to refraction only. And in wave optics, we study different phenomena such as interference, diffraction, and polarization. Now, these are topics. The topics related to wave optics is discussed in class 12, and in class 9 and 10 we discuss topics reflection and refraction. So before starting with refraction, you might all know that light travels with different speed in different medium. It travels with a different speed in air, it travels with a different speed in glass, it travels with a different speed in air, it travels with a different speed in water, and so on. So the speed of light is different in different medium. Different in different medium. However, depending upon the speed of light in different medium, we classify a medium as either a denser medium or rarer medium. Now, by saying denser or rarer, it has nothing to do with density of the medium. We actually say that a medium is either optically denser or optically rarer. Now, it is related to the speed of light. It has nothing to do with density. Optically rarer medium means that speed of light is comparatively more, and optically denser medium means that it slows down light, or the speed of light is comparatively less. So a denser medium will slow down light, whereas a rarer medium will speed up light. That means the velocity of light is comparatively lesser in denser medium, and the speed of light is comparatively greater in rarer medium. So if you compare the speed of light in water and glass, water is a optically rarer medium, so speed of light is less in water, and glass is optically denser medium, so speed of light is less in glass. So whether a medium is rarer or denser, it is on a comparison basis. If you compare air versus water, then air is rarer medium and water is denser medium. If you compare water with glass, water is a rarer medium, whereas glass is a denser medium. Now, when light travels from one medium to another, it does not follow its preferred path. the path of the light actually changes when it is at the boundary of two medium. So at the boundary of two medium, light suffers both reflection and refraction, provided the medium on either side of the boundary is transparent. If it is an opaque medium, definitely most of the light will be absorbed. But if light passes from one medium to another medium, definitely the speed of light will either increase or it will slow down, and so the path of the light will change. So as we are studying refraction only, but it is to be noted that when light travels in a straight line path that we always assume in ray optics or geometrical optics, when a ray of light is traveling in one transparent medium and it is incident obliquely on the surface of another transparent medium, a part of light is reflected back into the same medium and the rest of the light is transmitted into the other medium in a direction which is different from its initial path. So I can explain this by a simple diagram. Suppose this is the boundary that separates two medium. Now a ray of light which is traveling in a straight line from one transparent medium, suppose this is medium 1 and on the other side we have medium 2. So light or ray of light traveling in one transparent medium is incident obliquely. It is not incident perpendicularly, but suppose it is incident obliquely on the surface of another transparent medium. Both these medium are transparent, that means they allow light to pass through them. Now when light hits this boundary separating the two medium, a partial reflection occurs, that means some amount of light is reflected back into the same medium and some amount of light will be transmitted to the other medium, and light will not follow its preferred path. So the actual path of light was this dotted line, but light will either move away from this path or it will move closer to the perpendicular drawn at this particular point. There are two possibilities. So either light will bend in this manner or light will bend in this manner. Either of this is possible. Not both at a time, but either light will bend towards the perpendicular drawn at the point where the ray of light hits the transparent boundary separating the two medium, or light will bend away from the normal. Now, if we deal with both these criteria, as when light bends towards the normal or when it bends away from the normal, we define the medium, or we can say which medium is rarer and which medium is denser. So now this is the incident ray, this is the reflected ray, and either of these is the refracted ray. The incident light has some intensity because light is reflected back into the same medium. The refracted ray will not have the same intensity as that of the incident ray. Some amount of light might be also absorbed by the boundary separating the two medium. So there is loss in intensity definitely. The incident ray has the maximum intensity. The reflected ray and the refracted ray will have definitely loss in intensity, because on reflection there is some absorption also by the boundary separating the two medium. Because our focus is on refraction, let us, for the time being, assume that there is no reflected ray, but in reality some amount of light is always reflected back, and the if the boundary is transparent or the medium on both sides of the boundary is transparent, most of the light will be refracted and some part will be reflected. So we are considering refraction, so you can ignore reflection temporarily. So suppose this is the boundary separating two medium, and let me say that medium 1 is a rarer medium. That means speed of light is comparatively more in that medium, and medium 2 separated by this boundary is a denser medium, which means that it will slow down speed of light. A ray of light is incident obliquely on the boundary. At the point of incidence, we can draw a perpendicular, which is called as normal. This is the incident ray. It makes some angle with the normal. Let that angle be called as angle I, or the angle of incidence. I is called as angle of incidence. And suppose the ray of light moves towards the normal or bends towards the normal, then the angle made by this ray with the normal is called as the angle of refraction, R. This is angle of refraction. And this ray that enters into the second medium is called as the refracted ray. This is the incident ray, this is the refracted ray. When light bends towards the normal, then the second medium is denser and the first medium is rarer. So you can say that if a ray of light passes from rarer to denser medium, it will bend towards the normal. Now this angle that the actual direction of incident ray makes with the refracted ray is called as the angle of deviation, and let me denote it by delta. This is angle of deviation. Now if you see the diagram minutely, angle I is vertically opposite to R plus delta. You can say that angle I is equal to R plus delta. They are vertically opposite angles. So the angle of deviation in this case is I minus R. Now if a ray of light travels from denser medium to rarer medium, it will bend away from the normal. This we can show by a different diagram. Suppose we say that the medium 1 is a denser medium, and medium 2 is the rarer medium. Then the ray of light, when it enters the second medium, will bend away from the normal. So this is what will happen. Now the refracted ray is this one. It has bent away from the normal from its preferred path. Now this entire angle is the angle of refraction, and this angle is the angle of deviation. So now you can say that I is equal to R minus delta, because I is vertically opposite to this angle, and this angle is obviously R minus delta. So here you can say that I is equal to R minus delta, or delta is equal to R minus I. So there are two situations. When light is moving from rarer to denser, it bends towards the normal, and when light is moving from denser to rarer, it will bend away from the normal. When light moves from rarer to denser, the angle of deviation is I minus R, and when light moves from denser to rarer medium, it is R minus I. Now experimentally this has been observed, and there is a very popular law that expresses the principle of refraction, and that law is called as Snell's law. Snell's law of refraction. So according to Snell's law, which has been determined experimentally, it says that, or experimentally it was obtained that the refracted ray, the incident ray and the normal at the points of incidence all lie on the same plane. The incident ray, the refracted ray and the normal at point of incidence. Normal means the perpendicular drawn on the boundary separating the two medium at the point of incidence. All lie on same plane. Same plane. And the second law is that the sine of the angle of incidence, the trigonometric sine of the angle of incidence to the sine of the angle of refraction is a constant, and that constant is called as refractive index of second medium with respect to first medium. With respect to first medium. First medium. First medium. Which is expressed in this form. We use the symbol mu to denote the refractive index, and we write it in this manner: refractive index of second medium with respect to first medium. 1 mu 2 means refractive index of second medium with respect to first medium. So this is what we learned from Snell's law. Suppose this is a ray of light which has fallen or is incident obliquely on the boundary separating two medium, and if light moves from rarer to denser medium, then it bends towards the normal, and if this is the rarer medium of refractive index mu1 and this is the denser medium of refractive index mu2, we say that sine of angle of incidence by sine of angle of refraction is refractive index of second medium by refractive index of first medium, which is also called as refractive index of second medium with respect to first medium. This is rarer to denser, and if light travels from denser to rarer, this is what will happen. As I have already discussed, it will bend away from the normal. This is the first medium which is now denser, this is the second medium which is now rarer. So in this case, this is a rarer medium, this is the denser medium, and in this situation, this is the denser medium and this is the rarer medium. For example, light moving from air to water. First situation, light moving from water to glass, glass to water or glass to air. So these are the two possibilities that might arise in the principle of refraction, but you should remember the convention of applying the refractive index. The refractive index is a constant for a pair of medium. We shall define what is the absolute value of the refractive index of any medium, but for the time being we are discussing refractive index on a comparative basis, and that is the reason why I am saying refractive index of second medium with respect to first medium, or refractive index of first with respect to second, if light moves from the second to the first. In this case, I have shown that light is moving from first medium to second medium. You can also say that light can move from second to first medium. In that case, this index will change, and we will call it the refractive index of the first medium with respect to the second medium. In that case, Instead of 1 mu2, you will write 2 mu1. Now, as light moves from one medium to another, its speed changes, its wavelength changes, but its frequency does not change. So you can say that the cause of refraction is nothing but the change in the speed of light, due to which there is a change in wavelength. So cause of refraction is nothing but it is the change in speed of light due to which this principle will occur. So refraction occurs it is due to change in speed of light when it moves from one medium to another. And as speed of light changes, wavelength also changes. But remember that when light moves from one medium to another, its frequency does not change. So on refraction, you can say on refraction, speed changes, speed of light either increases or decreases, wavelength changes, but frequency does not change. Frequency does not change, it remains constant. So this is an important aspect of light or important property of light, and it is the change in speed of light due to which refraction actually occurs. Now, if we define the refractive index, we have to compare the refractive index with respect to that of vacuum. So refractive index, or the absolute value of refractive index of any medium, refractive index of any medium is defined as the ratio of speed of light. Refractive index I am denoting by mu. The refractive index of any medium is actually equal to the speed of light in vacuum to the speed of light in that given medium. Speed of light in the medium. If I denote the speed of light in vacuum as small c, and speed of light in the medium is v, then you can see that mu equal to c by v. Speed of light in vacuum is a constant which is approximately 3 into 10 to the power 8 meter per second. So you can say that refractive index is inversely proportional to the speed of light. That means if the speed of light is more, the refractive index is less, and vice versa. So in a rarer medium, the speed of light is more, so it has less refractive index. Whereas in a denser medium, the speed of light is less, so it has more refractive index. So when you compare the refractive index of glass versus air, refractive index of glass is more and refractive index of water is less, which means that glass is denser and water is rarer. Light will speed up in water as compared to glass. In glass, light will definitely slow down. But in mathematical analysis, sometimes we, instead of saying the speed of light in vacuum, we also consider speed of light in air. Speed of light in air is almost same to that of speed of light in vacuum. But ideally, the definition should be speed of light in vacuum to speed of light in medium. So you see that refractive index is inversely proportional to the velocity. That means if the velocity of light is more in a medium, its refractive index is less, that means it is rarer medium. And if the refractive index is more in a medium, the speed of light is definitely less. It is a denser medium. So when we are saying the refractive index of one medium to another medium, suppose I am saying refractive index of the second medium with respect to first, it means refractive index of second medium by refractive index of first medium. Whereas if I am saying refractive index of first medium with respect to second, this will be refractive index of first medium by refractive index of second medium. Now, on that basis, if I start comparing the definition and relate it to the velocities of light in the first medium and the second medium, then it will become like this. As I have already told, the sine of the angle of incidence to the sine of the angle of refraction is a constant which is called as refractive index of second medium with respect to first medium. Here I have assumed light is moving from medium 1 to medium 2. So this can be written as mu2 by mu1. Mu2 means refractive index of second medium. So it is velocity of light in vacuum by velocity of light in second medium. Refractive index of first medium is velocity of light in vacuum by velocity of light in the first medium, which is equal to v1 by v2. Now we know that for wave, velocity is the product of frequency and wavelength. So I can say that v1 is f lambda 1, where lambda 1 is the wavelength in the first medium, and v2 can be written as f lambda 2, where lambda 2 is the wavelength in the second medium. Remember that when light moves from one medium to another, the frequency remains same. So it is not f1 or f2, it is f. So therefore what we have is Snell's law is sin I by sin r, which is equal to refractive index of second medium by first medium, which is equal to velocity of light in first medium by second medium, which is equal to wavelength of light in the first medium by wavelength of light in the second medium. Now this, by practice, you can remember, and then on we can go through different examples where light speeds up and slows down. Suppose light enters glass from air. Now air is a comparatively denser medium, air is a comparatively rarer medium and glass is a comparatively denser medium. So suppose we write the refractive index of air as mu A and refractive index of glass is mu G. So obviously refractive index of glass is greater than refractive index of air. So the light that enters glass is obviously moving from rarer to denser medium, and so it will bend towards the normal. This is the angle of refraction and this is the angle of incidence. So by Snell's law, we write sin I by sin r is refractive index of second medium. Now this is the second medium and this is the first medium. So we write refractive index of second medium with respect to first medium. So this will be written as A mu G, which is obviously mu G by mu A. Suppose we take another example. Suppose glass versus water. So refractive index of glass is mu G and refractive index of water is suppose mu W. Now glass versus water, glass is denser medium and water is rarer medium. So a ray of light traveling through glass and entering water will obviously bend away from the normal because glass is denser and water is comparatively rarer medium. This is angle of incidence and this is the angle of refraction. So in this case we will write sin I by sin r is equal to refractive index of second medium with respect to first medium. So it will be written as second medium is water, first medium is glass. First medium means the medium in which there is the incident ray, and the second medium means the medium in which there is the refracted ray. So this can be written as mu W by mu G. So with respect to air, if you compare the refractive index of any medium, you can also express it in that manner, because the refractive index of any medium is actually the velocity of light in that medium divided by velocity of light in, refractive index of any medium is velocity of light in vacuum by velocity of light in any medium or in that particular medium. So in normal circumstances, the refractive index of air is very nearly 1, it is approximately taken as 1, and refractive index of vacuum is also 1. So in some mathematical calculations or numericals, sometimes refractive index of air is taken to be 1, but this is not perfect, it is an approximate value. The refractive index of vacuum is actually 1. Refractive index of vacuum is 1. Index of vacuum is 1. But remember, sometimes we also say that refractive index of air is 1. Because it is very nearly 1, we take it as 1. So we can compare the refractive index of any medium with respect to air also. So for example, suppose when we are comparing the refractive index of glass versus water. So refractive index of glass with respect to water is actually refractive index of glass by refractive index of water. Now this refractive index of glass, its absolute value can be written as refractive index of glass with respect to air by refractive index of water with respect to air, because this is nothing but refractive index of glass by refractive index of air divided by refractive index of water by refractive index of air, which produces the same result, this result. So you can compare on the basis of refractive index with air also in some situations where we assume that the refractive index of air is 1. We assume refractive index of air is 1, but this is an approximation. This is an approximation. So in textbooks, if you see that refractive index of air is 1, that means that is an approximation. Actually, the refractive index of vacuum is 1. Suppose a ray of light travels from medium 1 to medium 2. Suppose the ray of light, the incident ray is perpendicular to the boundary separating both medium 1 and 2. The incident ray is perpendicular. If the incident ray is perpendicular, no matter what the refractive index is, it will simply pass undeviated. It will simply pass undeviated. So in this situation, the angle of incidence is 0, the angle of refraction is also 0. The ray passes undeviated. Undeviated. So you can say that there are two situations when a ray passing from medium 1 to medium 2 remains undeviated. The one possibility is obviously the angle of incidence is 0. That means the incident ray is perpendicular to the boundary separating the two medium. And the second situation is that the refractive index I am writing as Ri, refractive index of medium 1 is equal to the refractive index of medium 2. Then again the ray of light will pass undeviated. The ray will pass undeviated. So these are the situations where the ray of light, when it passes from medium 1 to medium 2, remains undeviated. The situation 1 is the incident ray is perpendicular to the boundary separating the surface, and the second situation is if the refractive index of both medium 1 and medium 2 are same, then the ray of light passes undeviated. So refractive index is a property of a medium, and it certainly depends upon some factors, some physical factors. So the factors on which refractive index depends is obviously the nature of the medium. Factors on which refractive index of medium depends is obviously the nature of the medium. That means whether it is optically rarer medium or optically denser medium. By nature we means the optical density. Optical density, remember, it has nothing to do with density as mass by volume. It is dependent on the speed of light in the given medium. The second factor is temperature. Refractive index depends on temperature of the given medium. With increase in temperature, actually the speed of light in the given medium increases, and so the refractive index decreases. If temperature increases, speed of light increases. So refractive index decreases. Remember that refractive index is C by V. So if V increases, obviously refractive index or mu will decrease. The third factor on which refractive index depends is the color or wavelength. Color or wavelength of light. So refractive index, remember that refractive index actually increases with decrease in wavelength. Increases with decrease in wavelength. Decrease in wavelength. Let me call wavelength as lambda. So refractive index will increase if wavelength decreases. If you consider the colors of the spectrum, that is violet, indigo, blue, yellow, orange and red, you see that refractive index of violet will be definitely greater as compared to red, and in that order. So wavelength of red is approximately 8000 angstrom and wavelength of violet is 4000 angstrom. So you see that lambda or wavelength of red is greater than wavelength of violet. Now as refractive index increases with decrease in wavelength, so in this case refractive index of red will be less than refractive index of violet, and it will follow that order. So if you go from violet to red, the refractive index will decrease and wavelength will increase. So these are the three common factors on which refractive index of a medium depends. Now in the examples that I have taken, when light passes from one medium to another, I have assumed a monochromatic ray of light. Monochromatic ray of light. Monochromatic means of single wavelength or single color. So I have considered all the examples, and in those examples I have considered the ray of light as monochromatic, so that there is one incident ray and there is one refracted ray. But what happens if we take polychromatic ray or polychromatic light? Polychromatic means of many colors. White light is polychromatic because it consists of 7 colors of many wavelengths or many colors. The example is white light. White light comprises of 7 colors. The colors refer to what we can actually visualize. But if you consider the wavelength range, it is quite large. It starts from 4000 angstrom and it ends in 8000 angstrom. So if 1 angstrom is represented by one wavelength, then also you are having 4000 wavelengths at least, with a variation in the brightness and the intensity of the colors. Whatever it is, white light is polychromatic. That means it consists of many wavelengths or many colors. Now, if I consider a polychromatic ray, or say for example white light, suppose this is a polychromatic light or white light, suppose, consisting of at least 7 colors that we can visualize. And suppose the ray of light is moving from medium 1 to medium 2 with refractive index of the second medium greater than refractive index of the first medium. So that means it is denser and it is rarer. So obviously ray of light will bend, but as it consists of different colors, when the ray of light hits the boundary separating the two medium, the speed of different colors or different wavelengths are different. So they will bend by different amounts. Speed of different wavelength is different. Different wavelength is different. As the speed of different wavelength is different, so refraction is due to the speed of wavelength, the speed of the corresponding light ray, and as speed for different wavelengths is different, at the boundary it will deviate by different amounts. Obviously the ray of light will deviate towards the normal because I have considered this as the rarer medium and this as the denser medium. But if you observe minutely, then you will have many rays upon refraction, and the maximum deviation will be of violet. So if you consider the two ends of the pattern, then this is red and this is violet. Why? Because refractive index of violet is greater than refractive index of red, and hence deviation of violet, delta V, will be greater than deviation of red, and all the colors will be in between, and in between you will have many wavelengths and so on, which means that wavelength of violet is less than wavelength of red and speed of violet will be less than speed of red. So this is an important observation, and when we will study the chapter spectrum, we will again come back to this same point. So instead of taking monochromatic light, that means light consists of single wavelength, if you consider the refraction of polychromatic light or white light, then the light will not refract along a particular direction, but at the point of separation, at the surface of separation of two medium, as the speed of different wavelengths is different in a given medium, it will bend by different amounts, with violet bending the most and red bending the least. So this is an important observation associated with refraction of white light or any polychromatic light. Now we will look at another important point, that is the path of a light ray is reversible. Light ray is reversible. Now let us consider light moving from first medium to second medium, and suppose medium 2 is denser and medium 1 is rarer. So what we have already observed, we are considering monochromatic ray obviously and a single wavelength or single color. So this is the incident ray, this is the incident monochromatic ray. It is moving from medium 1 to medium 2, where medium 2 is denser and medium 1 is rarer. So now light will obviously bend towards the normal. Suppose we hold a mirror such that the refracted ray falls perpendicularly on the mirror. So you hold a plane mirror this is a plane mirror and it is held in such a manner that the refracted ray is perpendicular to the mirror. When the refracted ray is perpendicular to the mirror, then obviously it will bounce back in the same direction. This refracted ray is perpendicular to the mirror, so it will reflect back in the same direction. The reflected ray I have shown by double arrow. Now this ray after reflection will move along this direction. It will come at the boundary of separation of the two medium. Then it will again move along the same path as that of the incident ray. So this reflected ray, as it comes to the boundary separating the two medium, it will obviously follow the same path. This is the angle of incidence, this is the angle of refraction. Now you can realize it by applying Snell's law. So when light is moving from medium 1 to medium 2, the first situation, light is moving from medium 1 to medium 2, then you can write sin I by sin R equal to refractive index of the second medium with respect to the first medium. When light after reflection from the plane mirror is moving from medium 2 to medium 1, in that case you can write sin of, this will be the angle of incidence because light is moving in this direction. So this will be the angle of incidence and this will be the angle of refraction. So it will be sin R by sin I. Now this will be refractive index of the first medium with respect to the second medium. First medium with respect to the second medium. So this is for light moving from second to first medium. And this is the situation for first to second medium. So now if you multiply these two equations, you see that sin I by sin R into sin R by sin I, which is equal to 1 mu 2 into 2 mu 1. So this is obviously 1 because sin I and sin R will cancel. So what we have is 1 mu 2 is 1 upon 2 mu 1. This is also called as reversibility of light ray. The path of light ray is reversible. Now, for example, if you say that refractive index of glass with respect to air, suppose refractive index of glass with respect to air is 3 by 2, then refractive index of air with respect to glass, then by this principle of reversibility, refractive index of air with respect to glass will be 2 by 3. They are reciprocal of each other. So this is a very important observation and it says that the path of a light ray is reversible. Now we will study refraction of light through a rectangular glass block. So suppose this is a rectangular glass block and its thickness is T. A ray of light is incident on the glass block. Suppose this is the point of incident and this is the incident ray. This is the point of incidence, let me call it as point P. Because the ray of light is moving from, suppose, air, and this is glass of refractive index mu, suppose. Refractive index of air I have assumed as 1. So refractive index of glass as mu g, and refractive index of air, let me consider it as 1. So ray of light is moving from air to glass, so it is moving from rarer to denser, it will bend towards the normal. This is obviously the angle of incidence, and this will be the angle of refraction. And this dotted line is perpendicular on the surface. Now this ray will again hit the boundary separating glass and air. So now the ray of light is moving from denser to rarer, because obviously it is air here. So now the ray of light is moving from glass to air, so it is moving from denser to rarer, it will bend away from the normal. This angle is also R, because this dotted line is perpendicular to the glass block, and this dotted line is also perpendicular to the glass block, and they are obviously parallel to each other. So this angle is alternate to this angle, and hence this is R and this is R also. Now this angle is the angle of refraction when light passes from glass to air. This angle is now called the angle of emergence, because the ray is emerging out of the glass block. So this ray is called as the emergent ray, and this angle is called as the angle of emergence. So we have these angles. Angle I is angle of incidence, and angle E is angle of emergence. Now you observe that this is the incident ray which I have produced by this dotted line. The incident ray has been produced. The emergent ray will always become parallel to the incident ray. This you can prove definitely, but still before proving it, remember that the incident ray is parallel to the emergent ray. If you prove that this angle I is this angle E, then obviously it will be proved. So just remember, emergent ray will be parallel to incident ray. Incident ray. So if you apply Snell's law, you can easily prove that I is equal to E, and so the emergent ray is parallel to the incident ray. So this is the incident ray which has been produced, and if we draw a perpendicular from this point to the incident ray which has been produced, this length is called as the lateral displacement. So suppose this is point P, this is point Q, and the perpendicular is suppose QN, then QN is called the lateral displacement. So what we realize is that when a ray of light is incident on a rectangular glass block, and as it emerges out of the rectangular glass block, the emergent ray becomes parallel to the incident ray, and the lateral displacement depends upon three factors. The lateral displacement, this lateral displacement, it depends on three important factors. It depends on the thickness of the glass block, it depends on thickness of glass block that I have written as T. It depends upon the angle of incidence, I, and it also depends upon the refractive index of glass. It depends upon the refractive index of glass, that is mu g. So these are the factors on which the lateral displacement depend. it actually increases, lateral displacement you can say, it increases with increasing thickness of the glass block, it increases with or increase in angle of incidence, and it also increases with increase in the refractive index of glass. You can take different types of glass, you can take borosilicate glass, Pyrex glass, different types of glass are available. So if the refractive index of glass increases, lateral displacement will increase. If angle of incidence increases, lateral displacement will increase. If the thickness of the glass block increases, lateral displacement will also increase. So we can prove that I is equal to E. That means the incident ray is parallel to the emergent ray. This is the incident ray, which will be parallel to the emergent ray. So if I apply Snell's law, when light is moving from air to glass, refractive index of air, you can take mu A, later you can take the value as 1 also. So refractive index of air is mu subscript A. Ray of light entering from air to glass. So for the first situation, air to glass. Sine of the angle of incidence by sine of angle of refraction, that is sin I by sin R, equal to refractive index of glass with respect to air. When light moves from glass to air, sine of incidence will be now R, because this is the incident ray that is from glass to air. So this will be the incident ray and this will be the refracted ray. So by Snell's law, sin R by sin E is equal to refractive index second with respect to the first medium, that is air with respect to glass. If you multiply this sin I by sin R into sin R by sin E is equal to now by the principle of reversibility of light, we know that A mu G is 1 by G mu A. So sin I, sin R will cancel out. Sin I by sin R will be equal to 1, since G mu A is 1 by so this means they will cancel out, and you can see that the product is 1. A mu G into G mu A is 1. So sin I by sin E, sin R cancels out. So sin E by sin E is 1, which means sin I equal to sin E. This means that I is equal to E. So the angle of incidence is equal to the angle of emergence. This also means that the incident ray is parallel to the refracted